my great pleasure to introduce the 2018 Warren Awardee, Dr. Simon Billinge. This award is being presented to Dr. Billinge for seminal developments in study of nanostructure using atomic pair distribution function methods. Now, Dr. Billinge started his career studying materials as an undergraduate at the University of Oxford. He continued his studies in materials science and engineering at the University of Pennsylvania, studying under the guidance of Takeshi Agami, also a Warren Award recipient. So he's carrying on the legacy. Dr. Billinge is professor of material science and engineering and applied physics at Columbia University. So Dr. Billinge, on behalf of the American Crystallographic Association, it is my honor to present to you the Warren Award.
What I'm going to tell you about, if you're not aware of it, is the atomic pair distribution function method. We call it PDF method. And it's a way of using X-rays, neutrons, and electrons to study nanomaterials. And it's been around a very long time. I'll give you a little bit of history. But it's really taken off recently for a number of reasons, and that's what this series of fortunate events is. That's a little PDF in his eyepiece. So, firstly, on the Warren Award, it's actually a really incredible honor for me to receive this award. And there are three main reasons, apart from the obvious ones. So the first one is actually named for Bo Warren. I was unfortunately never able to meet Bo Warren, but just look at his picture. Who would want to meet this guy? It's actually my ambition to look like this when I'm his age. But he was a peerless pioneer in the field of structure of non-crystalline materials, which include nanomaterials, which has also been my passion. So his greatest contribution, this is from his obituary actually, which was in Journal of Applied Crystallography. His greatest contributions lie in his creation of mathematical experimental techniques for deriving information from the structure of matter, blah, 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 not necessarily restricted to Bragg reflections. And there's a quote that's attributed to him here that, as with humans, it's the deviations from regularity that are more interesting. This is a quote that I've used before, although it's also been attributed to Frank, who was a material scientist who studied defects in materials. So he was born in 1902, he died at 89, he was at MIT for his whole life. He was apparently a New Englander, he had a strong Boston accent. He was beloved of his students, and actually it turns out he was the second president of the organization that preceded the ACA, which, so we should all be grateful to the insightful people who did away with this as the Association of X-ray and Electron Diffraction. It's an absolutely impossible acronym to say. So this preceded the ACA. The ACA came to be in 1950. He was the second president of ACA, and he wrote possibly my favorite book of all time, which is X-ray Diffraction by Bo Warren, and I encourage you all to go look at it. The second of the main reasons that I'm so honored about this is actually, as Lisa mentioned, Takeshi Agami was my PhD advisor and mentor. He's a person that I still collaborate with and I'm highly honored to have interacted with over the years. He's another person who, like Warren, has a very great sense of humor and a very positive attitude about life. He taught me many things. He basically brought me from being a material scientist to being a physicist, gave me my love of non-crystalline materials. And I'm also honored that actually my most high-cited item is the book that he and I co-authored together called Underneath the Bright Piece, because that's where we think a lot of the gold is actually underneath the bright piece. And this was a picture taken at ACR in 2008 in Osaka, and there's a slightly younger version of myself. Sadly, I don't quite look like that anymore. And believe it or not, around the same time, it turns out that Takeshi was still making it into the finals of kickboxing events. This is him versus Daisuke Tsukishima Pancras. Actually, it's not him. I got some name confusion on Google, but yeah. Okay, so the third reason that I'm so honored to get this award, and I want to thank the ACA and the committee that awarded to me, is just look at the names on here. So these are the previous recipients, and there's a huge list of people on here who I've really looked up to over the years. I mean, there's Jim Jorgensen, who's a great guy in power diffraction, Bob Birchnow, Dale Sayers, Don Cowley, John Axe, David Price, Ian Robinson. So it's a slightly humbling thing for me to actually be able to add my name to this list. So I want to thank ACA and my nominators and the committee. So now a little bit about myself. So I'm currently now at Columbia University, which is in New York, and here's a picture of New York. And as you can see, it's mostly buildings, and there's a little bit of green here, and a little bit of green here. This is Central Park, this is Riverside Park, and there's a little bit of green there, and that's actually the campus of Columbia University. So if you come to New York, get in touch with me, and we can show you around Columbia. And this is a yellow circle around Columbia University, but this is actually my proposal for a synchrotron in New York City. And I've taken it to the mayor of the city, and it's in progress, but don't hold your breath. But because I don't have a synchrotron in New York, actually, I'm very fortunate that I have a co-appointment at Brookhaven, which is about 50 miles down the road on Long Island. And recently, 2014, they commissioned a new synchrotron there, National Synchrotron Light Source 2. Many of you probably also have used the NSLS, the original light source at Brookhaven. Okay, so when we do PDF, the reason we do PDF is because we want to study materials. And I want to stress the importance of materials and materials research. And this is a picture of actually some two people in front of the White House with a motorcycle. And according to Google, anyway, the year is 1915. And if you take a look at the materials in this picture, what you see is actually mostly natural materials. So his shirt is made of cotton, his pants are made of wool, his boots are made of leather. So 100 years ago, most of the materials we had were basically natural. The tire of his bike is rubber. There's some pretty fancy metallurgy going on here. So steel is already highly advanced already at this time. But everything else is basically natural. And he's got road cream instead. How many people in the audience know what road cream is? Oh, there's a few, yeah. So I put this into my talk. So I've given this talk before, obviously not this talk, but this slide. And I put road cream in, and this joke always falls flat because nobody knows what road cream is. But road cream is basically hair pomade. People in Britain used to put in their hair, and maybe in America, I don't know. And then I actually went to look up road cream. And it turns out road cream was developed first in like the mid-20s, so actually it doesn't have road cream in its hair. It probably has a natural product, which is probably oil for his body. So what else happened around 1915? Well, the only thing that happened around 1915 is a little before that, X-rays were discovered, and then people started applying X-rays to materials. And so this is the father and son of Bragg. And William Henry Bragg, the father, was the experimentalist. And it's 1913 here, and he's decided to start a new project, and he's starting a new lab notebook, and it's page 1. So this is actually Bragg's notebook from, it's in the museum at the University of Leeds, and they put it online, which is nice of them. And so they're starting out and looking at time. Basically, people back then did crystallography by measuring the angles between facets on crystals. So they already had goniometers, they already had ways of measuring angles, like orienting crystals in different ways and measuring angles between them. So this is a goniometer, they had this already. And all they did was they took the X-ray source and they pushed it up against the goniometer, and then they started their work. So here's page 1. And for the grad students in the audience, you should thank your stars, lucky stars that you're alive now, because back then they actually collected data by writing the numbers down with a pen. Okay, page 1. Oh yeah, so the experimental equipment was made of natural materials too. Wood, some fancy metals, and paper. All right, so we're up to page 11, and this is the world's first Bragg peak. So discovered Bragg peaks in page 11. And then this is the first structure solution here, page 43. So brand new notebook, 43 pages, Nobel Prize, bang. That's how it used to be. All right, so 100 years later, though, let's look at what the motorbike looks like now. And it's basically all synthetic. So what happened in that 100-year period was we went from natural materials to synthetic materials. And why did we do that? It's performance. This motorbike goes faster and is more reliable than the old motorbike. So the whole objective in material science is to develop materials which are suited to task and have very high performance. And it's no accident that the ability of solving the structure of materials coincides with our ability to develop synthetic materials. So structure solution is a key aspect in materials discovery. Now, as we move into the 21st century, we want more efficient photovoltaics, we want more efficient batteries, we want new sources of power supply, like this is a pen fuel cell, which could be used for powering a bus, for example, using hydrogen. And this is some fancy person's idea of what a photovoltaic could look like, which has high efficiency. And what's notable about these devices here is that the materials that we're using in them are very, very complex. They're not simple materials, they're complex materials. So the photoactive layer here has nanoparticles in it, and these inorganic nanoparticles covered in organic hair. And in this fuel cell here, you have an anode, a membrane, an electrolyte, a membrane, a cathode. So you have this hierarchical structured device on a macroscopic level, and then on a microscopic level, the anode looks like cauliflower and the cathode looks like cauliflower. And on a nanoscopic level, sitting on top of this cauliflower are platinum nanoparticles which do the catalysis, which help the chemical reaction which drives the bus. Okay, so it's this really complex, it's not your mother's crystal here. The kind of material that we need to solve the structure of now looks like cauliflower. So this is the challenge that we have. So real materials have a crystal structure, or sometimes they don't. But they also have a morphology. We need to understand morphology, its effect on the properties. They can have surface reconstructions, they can have surface terminations, they'll have interfaces, they'll have heterogeneities, sometimes they'll be multiphasic, they'll have all kinds of defects. And we don't really care about any of that unless it has an effect on the properties, but of course it does have an effect on the properties. So we're interested in quantum dots. These are inorganic nanoparticles for their optical properties. And the optical properties depend very sensitively on the presence or absence of surface trap states, which are structural defects in them. The photovoltaic performance depends on charge transfer and charge extraction. So we have to take a photon of light, we have to split an electron-hole pair apart, then we have to extract the hole in the electron. And all of that depends sensitively on the morphology and on defects in the material. Catalysis takes place at the surface, and so on and so on. And there's even emergent behavior that happens at interfaces. So you can take an insulator, and you can take another insulator, and you can put them together, and at the interface you can get superconductivity. So superconductivity is a property of a metal, but we obtain superconductivity by bringing together two insulators, and it's an emergent property that's taking place just at the interface. So the point about this is that defects are important, they affect properties. So when we study materials, it's not good enough just to get the average crystal structure. We have to go beyond that, and we have to understand in great detail about the morphology and about the defects. So 21st century crystallography, in some sense, doesn't really involve crystals. They might be part of the story, but they're only a part of the story. And we have to go well beyond that. So I'm section editor of ACA Crystallographic, section A, which is Foundations of Crystallography. And I just want to throw this up and say to you that in this room, we're all 21st century crystallographers. And I encourage you to think beyond crystals when you think about whether or not to send your papers to ACTA A. We very much welcome contributions which are not just pure old-fashioned crystallography. So please think about sending us your good stuff. All right, so if you are going to look at a nanomaterial, what are some of the challenges? Well, if you have a crystalline material and you make a powder of it and you put it on the X-ray diffractometer, you get a nice powder diffraction pattern. We're used to that. If you have a nanocrystalline material, actually, I'm going to show you the diffraction pattern of a nanomaterial that's closely related to this zirconium phosphate. It looks like this. Now, the question is, this powder diffraction pattern here is actually less complex than that one. It has fewer peaks. And from an information theoretic point of view, it means it contains less information. Now, the structure of the nanoparticle is actually more complex than the structure of the crystal. So this is the main underscoring challenge that we have for nanostructure determination, which is that we need to solve the structure of more complex systems with less information. How do you figure out, from an information theoretic point of view, how much information is in here? So if we assume these peaks are symmetric, which they may not be, you get roughly 3 bytes of information, 3 numbers from each peak: its position, its integrated intensity, its width. And so we have 1, 2, 3 well-separated peaks and 1 slightly overlapped peak. So we have about 12 bytes of information. So we can only really make a model that that has 12 degrees of freedom and slightly less because we've got information loss here. So that would be a very simple model. And we have to avoid the temptation to overinterpret that data. Okay, so I showed you a little bit earlier that on page 11 of Bragg's notebook, they discovered the world's first Bragg peak. But I just want to tell you that actually the real kind of the most interesting scatterings I've been telling you is not the Bragg peaks, it's the diffuse scattering underneath the Bragg peaks. And it turns out that they discovered diffuse scattering on page 5. So the real Bragg scattering is diffuse scattering in my opinion. All right, so coming back to the PDF, how do we do the PDF? So the PDF is actually just a powder diffraction measurement. We put a powder in the beam, we bring a high energy beam in, it diffracts off the sample and we get a powder pattern. And this is actually a powder pattern from a crystalline material, so we get Bragg peaks here. And then we make corrections for the instrumental effects and other experimental effects, and we do some fancy normalization, which I'll mention in a sec. And we get what's called the total scattering structure function. So this is just basically the diffraction pattern. And it looks like a forest of Bragg peaks here, and not like something you've seen before, maybe, unless you've done PDF work. And simply the reason is that we've measured over a very wide range of momentum transfer Q. And so this is like the d-spacing, this is like the diffraction angle. And if you do a conventional measurement with a copper K alpha source, you only get these peaks down here. But what we do is we use short wavelength X-rays or neutrons that we collect data over a wide range. And then, as we were taught 80 years ago, by putting this through a Fourier transform relationship, we get the PDF. And what we like about the PDF is it's a very intuitive function. On this axis here is a probability, and it's a probability of finding 2 atoms separated by some distance. And on this axis is a distance, that's the distance between the atoms. And this is an angstrom, and this is a 10, that's 10 angstroms, 1 nanometer. So it's giving structural information on the nanometer-like scale. So we like it because it's intuitive, and we like it because it's operating on the nanometer-like scale. And a little bit of magic that gives us that enhancement in the information content comes through the normalization. So this is actually a scattering pattern coming from a quantum dot, a cadmium selenide nanoparticle that has a 2 nanometer diameter. And what you can see is it's broad and it's diffuse, and it only has a few peaks, just like that other one I showed you. And it has a long, long, long flat part out here at high Q, which for years and years and years we were throwing away. But when we do the normalization that we need to do to put it through this Fourier transform, we have to divide the scattering by the scattering cross-section of the sample, which is the atomic form factor squared. And the atomic form factor squared is a smoothly varying function like this. And what we're going to do is divide the blue curve by the red curve. And what we get is a huge amplification of any signal that's down here. And so this is what it looks like after the normalization. So this is 1820. And if we go back and we look at 1820, it looked like the data were flat and there was no information in the data. But after we do the normalization, we see that there is information in the data. And if we measure with enough statistics, with good enough signal to noise, we can extract that information and we can use it for our structure determination. All right, so the challenge was that we had less information and we needed to solve a more complex structure. And what we've done is we've devised a slightly different experiment where we've got an enhancement in the information. So what happens to this frag peak? What happens to this diffraction pattern when we put it through that PDF approach? And it looks like this. So again, from an information theoretic point of view, we have much more information back again to play with. In fact, this thing that we saw down here is actually this part of the diffraction pattern. So once we've collected a pattern, we can get these PDFs. We can also model them. It's fairly straightforward. You put an atom at the center, and then you go out some distance, and when you find another atom, you put a delta function, and you broaden the delta function to account for thermal motion, so it turns into a Gaussian. And we go out further until we find another one, another one, another one. And we can build up the whole PDF from the model. And we have now very powerful regression programs that can do refinements and fits. So we can actually extract quantitative structural information from the PDFs. So this is all developed in the last 20 years or so. But the PDF history goes back much further. So it comes originally from the Debye equation, which remarkably was written down in 1915, which was the same time as that photo I showed you. So there's a picture of Peter Debye. And he's thinking about this Debye equation in that picture. I know that one with high degree of authority. And then it took another 10 years or so, but Zernicke and Prins actually recognized this Fourier relationship between this Debye equation and the real space atomic air density. So they wrote down this equation. So starting in 1927, there was this realization that you could measure a diffraction pattern using Debye equation and then Fourier transform it and get this real space air density. And it was only 3 years later that the first experiment was done, and it was actually done by Peter Debye. So he was a theorist, a great, great theorist. He was also a talented experimentalist. And then his Burt Warren starting to play around in this domain, starting in 1936. There's this picture again, and these are his PDFs. Now bear in mind that back in those days, they didn't really have computers, so they actually had to do a Fourier transform, which is a double integral, by hand using paper and pencil and a slide rule. So it was an incredible piece of hard work to just actually Fourier transform the data. Now, people started studying nanocrystalline materials, so the PDF was used for liquids and to some extent amorphous materials right from the 1930s. In the 1950s, people started looking at nanomaterials, and actually one of the pioneers of that work was Rosalind Franklin, who's also famous for her DNA work. And she was working in, right before the Second World War, and then during the Second World War, for the UK government, working in the department that studied coal. And then she moved to France after the war, and then she's continued her studies on carbon black. And if you go back and read her papers from the 50s, they're really, really wonderful. I did some work on carbon in the 90s, and I basically couldn't get more information out of my data than she got back in 1950s, which was a very humbling experience. So Burt Warren also actually worked on carbon black, it turns out. In the 1960s, actually computers came along, but the computers looked like this. This is actually a picture from the PDP-9 factory of digital instruments in 1967. So in 1967, they were developing the PDP-9, and these guys at MIT were actually applying modern digital computers to do PDF work. And they did actually the world's first RMC in 1968 using one of these things, which is pretty amazing. So the title of the talk was a series of fortunate events, and so I want to take you through them. So what I did is I went and I looked at Web of Science, and I put in a search for X-ray plus PDF or X-ray plus pair distribution function. And I wanted to see what came out. So this came out. So basically what's happening is everything's latent. There's essentially no citations at all up until 1990, and then it starts taking off and it goes up and up and up. So one reason for that is there weren't many citations. The other reason for that is that actually in the old days PDF was called RDF, so I'm actually cheating a little bit. But basically the citation rate for this method was kind of low. Now, in the early 80s, pulse neutrons came along, So I showed you everything up through the 1960s, but pulse neutrons came along. It was actually Takeshi Igami who recognized that pulse neutrons could be a very enabling technology for PDF work because they have a large flux of epithermal neutrons, which are short wavelength neutrons. So this is a picture of the IPNS that he was using, and I joined his group in the mid-80s. And so actually, the application of pulse neutrons to study nanomaterials of PDF was pioneered by Takeshi, and that's more or less when I joined his group. So that was 1980. Then he was also actually starting to do X-rays, but relatively low energy X-rays. This was with NSLS2, so these were 28 or 25 kilovolt X-rays. Sometimes we tried to push it up to 30 kilovolt X-rays at NSLS. And that's a picture of NSLS. And again, that was Takeshi's vision and insight. These new tools were coming along. He wanted to grab these new tools and apply to the methods he was interested in. So there's two fortunate events. A limitation of the kind of X-ray sources that we had at the time were that they didn't have very high energy X-rays, so they didn't have short wavelength X-rays, which limited the Q range we could measure, which limited the real space resolution. And I was now an assistant professor at Michigan State, and I was very anxious to actually resolve the difference between an indium arsenic bond and a gallium arsenic bond in a semiconductor alloy. And I thought that I was going to do it with pulse neutrons, but I was naive. It turns out there's this neutron resonance which prevents you doing that experiment. So I had to do it with X-rays, and I applied for funding, and I was turned down because you can't do that with X-rays because of the atomic form factor. So that's maybe it's like a red rag to a bull. So I had to go and do it. So we went to actually CHESS, which could give us these very high energy X-rays. And this is Stefan Kitcher, who I worked with at CHESS. This is Il Kim Jung, who was my graduate student. And we managed to do it. We got a PDF with a Qmax of 45 inverse angstroms, and we resolved those two peaks. And the other thing that I want to say here is that this is actually from the CHESS website. So it turns out that you can just take an aerial photograph and draw a circle on it, and then a real synchrotron appears. I just want to say that, make sure you understand. Okay, so around 2001, I've had a long relationship with ACA, a great love for this organization, and it was 2001 ACA time for PDF to make an appearance at ACA, so I proposed to organize a PDF workshop, and actually what happened is it went up to the executive committee, and so this is a cartoon that was drawn by Stacey Morrison and forwarded to me by Connie. And it was about the deliberations that were taking place at this ACA executive back in 2001, so they're all looking very, very puzzled and concerned. And then, does anyone know what real space pair distribution function methods are? So apparently in the ACA executive in 2001, we were off the map, we were not on the map. But actually their vision, the vision of that committee gave us the workshop, and we did the workshop. So that was another unfortunate event, and that was like right there. The other fortunate event was actually the world discovered nano. So the formation of the National Nano Initiative was actually 2001. And there's now a thing called nano.gov. So before that date, there was no nano, and then after that date, there's nano. So this is very fortunate because I had a technique that could study nano, and suddenly I had a problem that I could apply it to that was actually recognized by the US government. So that helped with funding. So that's another fortunate event. And then a technological development happened in the early 2000s. So this was work that we did together with Pete Chupas, who many of you may know, who went and built a PDF beamline and does excellent work at APS. But this was the rapid acquisition PDF development. So we would actually collect PDF data with a point detector, which we would move point by point up to a very high angle. It used to take 12 hours to collect one data set. And now we can collect a data set in a single shot like this. So our nickel data went from 12 hours to 1 second to collect a complete PDF. So that's a 4 order of magnitude increase in throughput. And so suddenly this went from a kind of a niche technique that only physicists could love to a utility technique that chemists could use to characterize their materials more or less straightforwardly. And so you can see actually this is the beginning of where it's really rising. And then finally actually some software developments that we're also involved with this is the PDF GUI, which then also made it easier to analyze the data and apply it to your problems. So that was 2000, mid-2000s. This is a group of people who actually put together PDF GUI, and so we have a nice GUI-driven modeling program. So suddenly this thing can take off. So this is the series of fortunate events, and I call it the perfect storm. We had the development of new sources, which we could leverage, and we had the development of new computers that we could leverage. This actually is an interesting picture. I gave an after-dinner speech at Oak Ridge last year, and the theme of it was going back to the 1950s. So what I did is I went back and I looked at 1950s pictures of computing, and it turns out that this is a picture that the RAND Corporation put out, and this was a mock-up, it's not a real computer. But this was their vision of what your own personal computer could look like in the year 1985. And they said every home could have one, and this is what it would look like. But I love this computer. It has a TV, and it has a steering wheel. I want a computer with a steering wheel. All right, so you must remember this. I showed it to you already. And this is what the PDF data looks like. But now we have data that looks more like this kind of information content. What can we start doing with it? And we can start looking at the real material. So this is a zirconium phosphate with phenol atoms. And what we have is these layers of zirconium phosphate, and they're joined together by organic groups. So this is what Abe Clearfield, who's another big person at ACA, he's calling them unconventional MOFs because they're metal organic systems, but they're really just layer materials where the tether is an organic. And you can imagine that these layers are pretty floppy, and these materials become nanocrystalline. But they're very interesting materials because they're very highly selective for 3+ ions. So Abe thinks that we can use this to separate lantanides and actinides in nuclear fuel reprocessing. And he wants to know why it's so selective for the 3+ ions. So you insert 3+ ions, you can interpolate 3+ ions into these layers here with very high selectivity. So this is Max, who you'll see more of, and this is Chen Yang, my students who did this work. But what we can do now is we can look at different structural morphologies or different structural connectivities of these layers, and we can compute the PDF from them, and we can compare it to the PDF we measure. And everything looks kind of very similar in the low R region because that's just telling you have octahedra and tetrahedra. The real difference between these competing structures is the connectivity, and that's kind of encoded in this high R region. And we can start differentiating these different models. And so this is what Chen Yang did. And he figured out that it was this one called phenol, which I can't remember which one it is. But anyway, we're differentiating between competing models to get the layer thing. But there's even more information about the morphology. If we take the PDF that we obtained from this material and we smear out the electron density in the metal layer, we get this smooth yellow line. So Max did this, and you see this beautiful zigzag line. This is actually a famous Warren line shape, which is the kind of line shape you get when you have a 2D object and you study it with power diffraction. So Warren makes his appearance again. And what it is it's actually showing the electron density distribution, the one-dimensional electron density modulation coming from these stacked layers. So it's telling us that even though we have a fair amount of structural disorder in the system, we have very well-ordered layers that continue up and up and up. And then we can fit models which don't have the layers in, and then we can actually see that the layer information is there. So we're getting information about the morphology. But what we really wanted to know is if you put this 3+ ion in, what's the local environment around the 3+ ion? So this is a really challenging experiment because we have a big signal from the framework and then a small signal from it's actually terbium. So these are two PDFs here. One of them is loaded with terbium, and one of them is unloaded. And you can see they're highly reproduced because they're very similar samples. But we take the difference between the red and the blue curve here, and we get the green curve. This has been blown up a little bit. So you can see that there's actually a signal left in the green curve. And that signal is the signal coming from the terbium, or the local environment of the terbium. So it's atomic correlations between terbium and the framework. And so what we can do is we can do simple things. We can, again, this PDF is such an intuitive function. We can say, well, there's a high probability of finding an atom at this place, like 2.5 angstroms away from the terbium, so that's terbium to oxygen probably. And then this one here is the terbium to phosphorus. We can infer that. But actually we have this full signal, and what Max was able to do was again to take competing structural models that he took from, he looked at databases of terbium phenolic, terbium phosphorus compounds, and he found different candidates. And he finds an amazingly good agreement with one of these that goes all the way out to 12. So that basically tells us in a high amount of detail exactly what the local environment of this terbium is. It's highly specific. And it's actually looking like this, so we can extract what it looks like in the material. So this is just a beautiful example of the hierarchy of things we can do. We can get the gross structure of the layers, we can look at how the layers stack, but we can also get details about how ions interpolate in. And bear in mind that these terbium ions are not periodically arranged, so there's no crystallographic solution that can do this. We've been pushing recently into the world of organics. I didn't think that PDF was going to have a role to play in organics because I thought organic chemists knew where their atoms were. They know what their molecule is. But it turns out that in a solid state, there's things to do. So what we started doing is looking at very rigid molecules. This is quinacridone, which is actually a commercial dye material. So it has beautiful colors, and the color changes depending on the crystal form. So that's another example where you take the same molecule, but you pack it differently in space. You get a different color. It has a different industrial application. But we ran into a problem, which is the following. Where we try and do a fit here, we have two regions of the PDF. The low R region is the intramolecular PDF. It's the PDF coming between atoms on the same molecule. And the high R region is the intermolecular PDF. It's the PDF coming from an atom on one molecule correlating with an atom on another molecule. Now, the molecule itself is covalent, so the bonding is very, very stiff. So the interatomic peaks are very, very sharp. On the other hand, the intermolecular part, the bonding between the molecules is weak. It's van der Waals, or it might be hydrogen bonding. That's much, much lower, much weaker than the covalent bonding, which means that the peaks in the high R region are much broader because there's much more disorder and variability in the packing. Now, when you do crystallography, you don't actually see any of that because you only see the intermolecular correlation part. And so it's a diffuse scattering underneath the Bragg peaks that gives us sharpening down here. But now we have a problem and we want to try and model these things. And so actually, we thought about this a long time, and together with Martin Schmidt, who was a collaborator, but a lot of the insights are coming from Pavel, who's here in the audience. We came up with this approach. So what we can do is we can calculate the PDF of the molecule. Here it is. And you see that it ends here because the molecule is finite size. We can calculate the PDF of the crystal structure because we know it. And it's here. And this is the PDF of the molecule when we calculate it using the crystal structure model, using an appropriate ADP for the crystal structure model. And so this is what it looks like when it's sharp, and this is what it looks like when it's broad. So what we do is we take this guy and we broaden it until it looks like this. And then we subtract this one from that one. So now we have just the intermolecular correlation part, and we have the intramolecular correlation part. So then we add A, and we add this one to this one, and we get this, which has now sharp peaks for the intramolecular part and broad peaks for the intermolecular part. And then it's straightforward then to do good fits, which give a good agreement over the whole range. So there's Pavel, and Dragica is the collaborator with Martin Schmidt's group. So we now have a way of actually modeling organic materials in a reasonable way. So another interesting thing is when we have our organics, we're actually, if you've got a crystal of your organic, you can do crystallography, you don't need us. So our value added is when you have actually nanocrystalline organic, or amorphous organic, or liquid organic. And when you have that, you actually have different kind of conformations present in your system. Now, when you have different conformations, we have a flexible molecule now. Part of the PDF is the same, but part of it changes. because the different conformation gives you different interatomic distances in your molecules. So this is Liz, who's my current student, who's working on this molecular conformation problem. And this is just showing for this molecule that if it's in two different conformations, it gives you different PDFs. And so what you can do is you can actually calculate PDFs for every different conformation. So here we've got a molecule which has a single rotational degree of freedom in it. We calculate the PDF in different places. So this PDF here is this guy and this guy. So the blue one is this one, red one is this one. And here again, you can see these different things here. So what we can do is we can actually start studying the conformational distribution of molecules in your signal. So that's something that Liz is doing. And so the tools are not actually published for this work yet. So this is just a little bit over the horizon, but it's coming down the pipe. We have a lot of interest from the pharmaceutical industry because they have a problem that a lot of the molecules they have in their drug development pipeline are highly insoluble. And they actually want to nanosize, they want to make pills that you can ingest orally, and they want to nanosize them to increase the solubility. And when they nanosize them, they can't actually characterize what they've got in terms of their molecules. So this work is pushing in that direction. And I think that will be a big growth area moving forward. Another thing that came out of our interactions with the drug industry was actually the ability to study PDFs at a much higher dilution level. So in the old days, people would say, how much do I have to have in my material to be able to see it? And we'd say 5% we can see it, 1%, you know, maybe. But we were doing this project with GSK, and they had a drug which was an inhaler drug, and it was a nano-sized drug which was in suspension in liquid that you inhale. It's anti-asthma drug. And this is actually the dosage form, 0.25 weight%. And so what we did is we did a PDF. We had a beautiful PDF of this is the signal. It's been kind of expanded, but this is what the signal looks like. And it looks like noise. But then we can notice this is the 5% weight% of the drug. But this is actually 0.66 weight%. And you can see we're reproducing the signal very, very beautifully. And finally, 0.25 weight%. So we can actually, it was a big surprise to us, and it came about because of some software developments that we've been doing. And we hadn't intended the software developments to do this, but they did this. So we can suddenly look at very, very small signals, 0.25 weight% of an organic in water. So we're very excited about this. It opens the door for all kinds of studies. So this is a study that Matt Sen went on to do, which is actually looking at recrystallization of lactose. So lactose is used as an excipient in drugs. It's the packing that holds the pill together. And if you've got an amorphous drug and you want to embed it in an amorphous matrix, you want to use amorphous lactose. And so our collaborators paid a lot of money to get this amorphous lactose, and then it would ship to their lab, and then it would recrystallize in their lab. So they just could have bought the crystalline form much cheaper. So they were kind of mad. And anyway, what we wanted to do was study the recrystallization. So this is amorphous lactose. This is the lactose molecule PDF, and the intermolecular signal is kind of flat. And then this is undergoing an enhanced aging. So after 1 minute under these conditions, it looks like this, 1.5 minutes. And you can see a little signal starting to pop up here. So it's starting to recrystallize, 2 minutes, 2.5 minutes, 3.5 minutes, the signal's getting more robust. 5 minutes, bam, it's gone. And then you leave it for longer, it stays crystallized, so it's irreversible. And so what we wanted to do is actually study what this pre-crystallization product is. We can look at the kinetics is one thing we can look at. So the amorphous material made different ways. This is the commercial one. This one lyophilized is freeze-dried if you're not a pharma person in the audience. And we had a melt quench one which actually never recrystallized. So this is a very stable amorphous form. We actually think that the presence of water in the material is actually like a lubricant for the recrystallization. But what we can do is we can look at the signal here, we can blow it up. So this is the 1 minute signal, and it's very noisy, but there's actually features there. And then 2.5 minutes, what we can see is the features are kind of growing, and 3.5 they're growing. And what you can also see is that this area is flat, so this is telling you the size of the nuclei. And then you can see the peaks are appearing at higher R, and the peaks are appearing at higher R. So the nuclei are growing. but they all have the same structure. But when you recrystallize, if you look carefully, this is the recrystallized form, and actually the peaks are in different places. So the first thing that forms is actually a different crystal structure from the final thing that recrystallizes out. So this is like Ostwald's rule of stages, which is that it's going to pre-form in the most, well, what Ostwald said is in the least thermodynamically stable polymorph will form first, and then it will go through stages to the most stable polymorph. I think that's basically rubbish because it's all about kinetics. So it's the most kinetically accessible form will form first, and then finally will go to the stable form. But so this is the kind of thing that we can now do, where these tiny signals we can actually make sense out of. So now we can actually do really fun things as well. So actually this is another thing where Max is looking at now a fairly flexible molecule here. This is again with GSK. And what we can find is we can find mutually as the molecule, and then we can treat these as intramolecular correlations of the subunit, and then look at the relationship to the other subunits. And so you need different ADPs between these different subunits, so we can start looking at the flexibility of the molecules in much greater detail. And the other thing here was actually he had two different forms of this amorphous drug. One was microfluidized. It was made by microfluidization, whatever that is. The other one was cryomilled. And you can see that they reproduce each other incredibly well. So they have essentially the same structure. But if you take the difference curve, you see this. And if you blow this up, you see this. And this peak here is actually a hydrogen bond peak. It's the oxygen to nitrogen distance in the hydrogen bond. And so we're pretty amazed about this. We can actually show that there's a slightly modified hydrogen bonding network between these two amorphization methods. Because we're using, what's happening now is I'm starting to show you some of the capabilities that are emerging and pushing into the future. And I'm still okay, I'll just go quickly. So we have very penetrating radiation because we use hard X-rays. It means we can do in situ experiments. So this is actually a PEM fuel cell that we can put in the beam and run the PEM fuel cell and then study the local structure. And we can extract the coarsening of platinum nanoparticles as a function of cycling in the PEM fuel cell. So in situ experiments become very, very feasible. We coupling together in situ experiments with our ability to measure dilute species. This is Kirsten Jensen, who was a postdoc in my group for 2 years. She's now assistant professor in Copenhagen, and she, with Bo Eisen's group in Aarhus, we were doing in situ synthesis in the beam. So we can actually do synthesis in the beam and see what kind of nanoparticles emerge. Because we can measure these very small signals, we figured out that we could do actually thin film PDF in normal incidence. So what we do here is we have a substrate, and the material of interest is actually a film. And there's two PDFs here. The red one is just the substrate, and the black one is the substrate with the film on it. And there's a tiny little difference curve. And we blow up the difference curve. We have good signal to noise, good reproducibility, and we can actually get the structure out. And we verified that. This was actually an amorphous film on an amorphous substrate, blue and red. Green is the difference curve. This is the difference curve blown up. This is actually the G of R from the thin film in red. And from a standard PDF where we made the poor grad student make like 20 of these films and then scrape the thin film off into a powder and then load the powder in a capillary to a conventional measurement. But you can see that we're really getting the right signal out from the thin film. So we can look at thin films. The smallest thin film is less than 100 nanometers thick that we've been able to measure the signal from. Once you can do normal incidence thin film PDF, we can imagine doing kind of lab-on-a-chip experiments where we actually make a chip and it has patterned on it different compositions and different chemistries, and we can just simply measure as a function of position. And so what we did here, this is a piece of carbon paper which has had different nanoparticle samples inkjet printed onto it at different locations. And then we simply do our normal instance thin film PDF and we raster across the film and we get a spatial dependent PDF map. This is a Pearson correlation map of this showing that you have the samples here, but these things are actually complete PDFs in each pixel, and we can do a fit to them and get structural information. And then what we did recently was take this one step further and combine it with computed tomography. So what we can do is we can take a 3D object. In this case, it's a catalyst body with nanoparticles, palladium nanoparticles on it. And we take 100 data sets as a function of position across here. Then we rotate it 2 degrees, we take 100 more, 2 degrees, 100 more. So we have 100 by 100, 10,000 data sets. And each of those data sets is a sum of all of the scattering through that region of the sample. But you apply the tomography and it produces 10,000 pixels. And inside each pixel we have a complete PDF, which we can then model. So this is actually a very beautiful spiral wound nickel metal hydride rechargeable battery. We simply took this battery, we put it in the beam, and we did this CT-PDF. And you can see this is the cathode, this is the anode, this is steel, so we can see the outside edge of the steel packing, but there's also a dotted line in there, spiral wound dotted line, because they load the cathode, they load the anode onto a metal mesh. So these are the kind of things that we can do, and this is one reason why the method is taking off. It has many, many applications, and there's many problems. So coming back to this, does anyone know what real space code addition function methods are? This was 2001. So I think it's crystallography for the 21st century. This would be my message. So just to summarize, modern materials are complex. Crystallography has to be beyond crystals. But modern synchrotrons are bright. Modern computers are fast. So use PDF and avoid fake news. Before I take questions, just let me thank some people. So I thanked all the people on the slides themselves, but I have really wonderful interactions with the synchrotrons and with the facilities. We depend on them enormously, obviously depend on funding. And I have a wonderful group, wonderful students. It's sunny in New York, they're smiling. But be careful if you want to join my group, because this is more the reality. Okay, thanks very much.
Are there any questions?
I wonder, from the example you gave on the difference in hydrogen bonding, and for those two cases, how do you feel about the concept of polyamorphism?
Yeah, so polyamorphism is an interesting one. So if you mean by polyamorphism, you can have two amorphous samples that have different structures, then it's fine. I'm with it. I believe it's true. If these are distinct phases and there's a kind of phase transition and regions of phase stability, I'm not so sure that that's been established in most cases, yeah. But yeah, I for sure, they can be polymorphic. Yeah. Okay.
So that's quite a body of work. It's really absolutely terrific. It was a terrific talk. So one of the things that surprised me most about it was this ability to measure things in organic at such a small weight percent so reliably, apparently. So can you say a few more words about that? So how do you sort of extract that from the general solvent signal? And then
yeah, so it's basically a signal to noise issue. So we were always feeling that we couldn't do it because you count for longer, you get more counts, but you're getting more counts from the solvent as well as from the signal. So you just simply have to hit it with enough photons that you get your signal to noise. Even with this very large background signal, you get your signal to noise to be in the right place. And the other thing that happened was that these are very sensitive difference measurements. So we would measure the empty solvent and the filled solvent, right? And the thing that was limiting our ability to differentiate them was actually our ability to reproduce the measurement exactly. So we would have a capillary, and the beam would have to hit the capillary would have to be the same. We'd have to hit the same part of the capillary. And that was actually what was limiting us. But the new software that we developed was to actually do an ad hoc correction for the fall off in the intensity coming from these effects. And that actually surprisingly corrected these differences and allowed us very, very small signals to emerge that we couldn't see before. So you need just very powerful sources and then good software.
Have you ever seen in any of your work on that sort of specific solvent solute interactions? Like, so
Yeah, so that's starting to emerge. Actually, we're not leading the charge on that. There's some work in Germany where people are seeing solvent restructuring. So the solvent molecules themselves. So one thing you can do, well, some work in the UK has been done over many years by Jan Sokol, where he's used ways of looking at the relationship between a solute and its solvent. And we're also beginning to be able to see solvent restructuring, which is showing how the solvent itself changes its density locally to the solute. Yeah, so it's coming. Yeah.
Any other questions? That's it. Thank you very much and congratulations again.
Thank you.